aquaponics. Who here has some familiarity with aquaponics in some sense? Okay, so that's great. We have a pretty decent number of people that know what it's all about. Like I said, I'm the president and co-founder of a company that's down in Loveland, and our focus is on developing components for commercial scale aquaponics and unleashing commercial scale aquaponics on a large scale. Here's the topics presented today. We're going to go through a little bit of an introduction and background for those of you that are kind of new to aquaponics. Talk a little bit about the technical background, the industry history, the pros and cons of aquaponics, and then we're going to talk a little bit about what we do, and then current exploration. So this might surprise some of you to find out that there's actually no formal definition of aquaponics out there in the Webster's dictionaries or any of these dictionaries that are out there. So we kind of made our own. And we define aquaponics as an integrated form of recirculating aquaculture systems, usually finfish farming, freshwater finfish, and hydroponics. These two systems are integrated together. In these systems, plants from the hydroponic component utilize nutrient-rich fish waste and fertilize as a fertilizer. In doing so, the plants sequester that fish waste and make that fish-bearing water sustainable for fish to be grown out in, and we recycle that fish water back in the fish-bearing component. And just so you guys have a basic picture, for those of you who don't know what aquaponics is, you have a picture of what it is. Every aquaponics system has at least two components, the fish component and the plant component. And in this case, this is a UVI-based system, University of Virgin Islands. I'll explain what that means later on. What that basically means right now is that there's plants grown in these rafts, these styrofoam rafts, and they're in deep water culture. There's culture in the water. And you have a fish component right there, which is raising the animals. Another type of system is a substrate-based system, where you have a media, like a rock media usually, that houses the animals and that acts as a biofiltration mechanism. And then the animals are, it houses the plants, and then the animals are housed inside the fish-bearing unit. These are just two small-scale systems to give you a picture, kind of a flavor of what aquaponics is. Here's a diagram describing what takes place. It all kind of starts with the fish feed and the fish. So these fish are producing ammonia. We know for a given fish feed content what the protein and the fat is, and we're able to determine from the protein content how much ammonia is being produced. And as a result of that, we try to process this ammonia in a very efficient manner, biological manner. We use bacteria to convert the ammonia, just probably a lot of you are familiar with this, biological filtration mechanism, to convert the ammonia to a readily available form of nitrogen to the plants. The plants then sequester that nutrient-rich water, and they sequester the nutrients from that water. They grow their fruit or their vegetative growth, and then that water is returned back into the fish-bearing unit, usually aerated beyond that point. So that's a real rough depiction of what that is. Here's another more detailed diagram of what's taking place, and I think most of you probably have some familiarity with this. The fish are generating ammonia. The ammonia is being processed by these ammonia oxidizing bacteria, the nitrosoma bacteria. They turn it into nitrite, NO2-, which is the most toxic form of nitrogen. I shouldn't say the most toxic form. Nitrogen gas is very toxic. You need to see that. But it's a very toxic form of nitrogen. But however, that form of nitrogen is removed very fast, very quickly by the nitrobacter bacteria, these nitrite oxidizing bacteria, and they turn that into nitrate, which is now one of the most readily available forms of nitrogen to plant production. Now, there's a lot of other processes that are taking place, a lot of microbial, bacterial processes that are taking place that are converting other nutrients besides nitrogen into readily available nutrients for the plant matter, or for the plant growth. But this is the one most people seem to focus on. And obviously, nitrogen is the primary nutrient component inside that fish effluent. Typically, this is kind of, down here, these are two graphs that kind of explain what takes place as you start an aquaponics system, as you inoculate an aquaponics system. It kind of describes the processes that are taking place in another diagram, which is, your ammonia spikes first as you start producing more and more waste. The fish waste is compounding. There's no bacterial processes removing that ammonia from the system. And then what happens is eventually you start to build up a large enough biofloc or a large enough bacterial culture that they're able to process that ammonia into nitrite. And then you start to see a decrease in the ammonia and a spike in the nitrite. Now the nitrite's really, really toxic, so you don't want to really see a spike this large. This is just here for representation. As the nitrite oxidizing bacteria start to grow in population, then you start to see a small trend, which ends up becoming quite large in the growth of the nitrate. And as it turns out, this is a depiction of what takes place for a lot of systems. Although what we'd like to do is we'd actually like to bring down the nitrite spike and even play around a little bit with the ammonia spike, because the nitrite is actually more harmful than the ammonia. And so what we've done, this is a year back now, over a year. We actually saw that we had a huge ammonia spike, but a very, very modest nitrite spike, which is a little bit more favorable for getting these systems up and going. And actually, as it is right now, there's a lot of research out there on how to fishless cycle systems, get systems established with this bacterial culture and ready to go so you can put the fish in directly without having to see these nutrient swings, which are really detrimental to both the fish and the plant health ultimately. So there's ways around this whole process now, but I just think it nicely displays what takes place here between the different stages of the bacteria. And feel free to interrupt me at any point if you guys have any question about what's going on. This is a little bit more for the biochemists, the people that are interested in biochemistry, what's taking place here. These nitrostoma bacteria take this ammonia, and this is probably a stoichiometric equation that some of you are pretty familiar with. They take this ammonia, they take hydroxide, and they take oxygen. They're aerobic bacteria. And they process that, and they convert that ammonia into nitrite, NO2 minus, and also they acidify the water. The next process now would be done by the nitrobacter bacteria, which take the nitrate, NO2 minus nitrite, and also oxygen for respiration, and they convert that into nitrate. Now that's the form of fertilizer that the plants prefer to take up. The plants prefer to take up nitrate in some cases because they're also able to take up positive ions as well, which is the form of a lot of salts that they're requiring, the calcium, the magnesium. So but the plant is required to stay electrostatically neutral. That's how it governs itself to all its biological processes. So if it takes on nitrate, then that means it's also able to take on other salts that are positively, they're cation salts, without having to eject an electron, or in some cases a proton, to stay electrostatically neutral. So it's a favorable mechanism for the plant to take up this nutrients in the form of nitrate. So the overall nitrifying bacteria reaction is ammonia plus your carbon, which is in equilibrium from carbon dioxide that's inside the water, plus oxygen, to form a hydrocarbon, that's part of the bacteria's cell structure. It has to get carbon from somewhere, and these bacteria are heterotrophs, which mean they consume their carbon from an outside source. Autotrophs usually eat other types of bacteria and things like that, other types of organic waste. With these heterotrophs, they have to take it from other means, so they take it actually from the carbon dioxide, and they sequester that into their bodies for their cellular structure. So is that clear? No, that got a little nerdy for a second. Okay, so we get the carbon from the bicarbonate source. Okay, a little bit about the research history. Most aquaponics knowledge has come from the University of the Virgin Islands. There's a few other really great universities out there that are doing some scale larger systems, but Dr. James Riccozzi was kind of the grandfather of aquaponics. He ran these systems for a number of years and demonstrated that they had commercial viability in his market, which is an island market, obviously. It's in the Virgin Islands. And what his system looks like is these are two pictures of what his system looks like. He has multiple rearing tanks, a whole bunch of filtration mechanisms, which we'll get into better detail about in a second. And the hydroponic component of his technology, or our technology, I should say, is a raft culture, which is very, very common today, and it's kind of what we call, amongst ourselves, the first generation aquaponics systems. That's really where aquaponics got started. It showed viability in using raft culture techniques. Here's a schematic. Has anybody ever seen this before? Okay. Here's a schematic of the UVI system. I'll go through how the water flows and what takes place. We have multiple rearing tanks, and the idea behind that is we want to keep a consistent nutrient source for the plant growth. And so if we have only one rearing tank every single time we harvest, we restock, there's giant swings in nutrients, and the plants are going to be suffering from that as a result. Actually, to a certain degree, the whole system suffers because the whole biodynamic element of the biofiltration changes as well, according to load. So yeah, there's multiple rearing tanks. Water's drawn from these rearing tanks. You guys are pretty familiar with circular tanks, I imagine, circular tanks. They draw from the bottom drain, and these heavy, really dense liquids that come from the effluent, which have a lot of solids, go to these clarifiers. These clarifiers right here are using different types of baffle, and they've actually experimented with a number of different systems. They've used baffles and substrates, all kinds of different things that try to cause solids to settle out or to be restricted. And then the water goes into these, what we would call today a bioreactor tank, which is biological filtration. It's a media-based tank, which has a substrate where the bioculture grows on. These nitrosomal and nitrobacteria grow on this substrate, and they convert all that fish effluent into fertilizers in that component. Now this takes place all across, that process takes place all across the whole system, because the whole system has a lot of surface area for bacteria to grow on. There's definitely reasons why you'd want to keep the bacteria centralized though, or located in a specific location, because there's a whole art and science to managing the biofloc, managing that bacteria. So we said water goes from these tanks, gets the solids removed right here, and to some degree also here in the biofiltration, to a large degree it actually does. And then nutrient-rich effluent water, which has removed solids, goes circulating through these raceways. They start at the head, they go down to the end, and then back through. These are pretty long raceways. And then they drop into a sump, which is this container right here, and they're re-aerated. There's a mixing chamber, which they supplement nutrients inside the water through that mixing chamber, and then it gets mixed right back into the fish container. And so for some of you that are interested in what I'm showing you here today, there's references to everything, and here's some of the details of the system. I'm probably not going to go over, but I'm happy to answer any questions about it. So a lot of people are asking, what are probably the benefits of the system? What are the benefits of aquaponics? So the first thing is to reduce water consumption. These are recirculating systems. So they're very, very low water usage in most cases. Recirculating systems, there's a technical definition for what they should be. You probably taught it. A lot of people say 95%, 90% water reuse. These systems can do quite a bit better than that, but and that's mainly attributed to the fact that it's taking up a bunch of micronutrients that are inside the water that wouldn't otherwise be biologically filtered out without phytoremediation techniques, which are planting techniques, plant growing techniques that remove these salts, these compound salts from the water. So it utilizes quite a bit less water than conventional fish farming or crop production when we consider this to be hydroponic or conventional. They say that it's only 10% the amount of water it requires to grow a crop conventionally in soil-based systems. That's a very commonly thrown out number with only a few substantiated people, a few substantiated groups that can claim that. It's actually more water. It considers more water than hydroponics as well, and I don't know if anybody here is familiar with hydroponics, but in the case of hydroponics, you're trying to continually keep a sterile environment. You want to keep all pathogens low. And the idea is that because it's so sterile, if you have a pathogen outbreak, it spreads quickly. There's no biodiversity to compete against that pathogen. So with aquaponic systems, you have a great deal of biodiversity. That's actually what you're trying to promote. You're trying to promote all these biomimicry techniques that take place in nature. And because you have such a resilient system with such great biodiversity, you don't need to exchange the water very frequently. You don't need to dump water like you would in a hydroponic system because of compounding algae and compounding pythium, root rot, and different things like that. So it uses significantly less water, and in most cases, water is the limiting resource for any kind of crop production, whether it be, it doesn't really matter, any kind of crop production. Oh, not that way. Oh. Let's see what's going on here. Jump like 100 slides ahead. Let's see here. We'll take it from here. Okay. So that's one of the benefits. So the other benefit, as I just said, could be successful in non-arable land. This is not just from a water consumption standpoint. You know, this whole technique cultures plants in a substrate that's inert. So you don't necessarily need to have even real soil to grow in. You know, a lot of places are just sandy or too loomy to grow in, so you can take this technology to them. A lot of places have limited resources in terms of the amount of nitrogen that's available, amount of fertilizers that are available to them, whether it's from natural mechanisms or whether it's transported in. It's no longer available to them. There's a whole technology that can service the whole demographic of people. Okay, significant demand for chemical fertilizers resulting from a nutrient-efficient bioreactor component which converts fish effluent waste into readily obtainable plant fertilizers. So we focused a lot on nitrogen, but there's actually a lot of other macronutrients, a lot of nutrients that are inside these systems that need to be processed in a way that makes them available to the plant. Nutrients that are compounded organically, or organically bonded, are no longer available to the plant in most cases. In fact, I can't think of a case where it is. You have to generally mineralize nutrients to make it available to the plant, or kind of break it down, decay this nutrient. And this process takes place within these bioreactors, which are focusing on the bioreaction of nitrogen, but they also support an environment for other types of bacteria that are actually a lot less common because there's a lot less food available. So they're common in lower concentrations, but they're always present. And so the idea is that these bacteria, and in some cases it's not even bacteria, some cases it's macroorganisms, worms and different things like that are making available calcium, iron, phosphorus from all the inputs that go into the system. Okay, so it's a closed environment, and this means a lot for environmental sustainability. You know, we're minimizing the amount of pathogens that are coming in which by putting into a greenhouse, and that results in using less fertilizer, using less pesticides. In fact, we never use any synthetic pesticides. We make all of our own stuff out of oils and different types of plants that we grow actually on site right there. And we've been able to manage our pests pretty effectively that way. But we're no longer using pesticides, and the reason why you can't use pesticides is because we emphasize the importance of the biodynamic environment you need to be creating. If you add pesticides to these environments, you could potentially be putting something out of whack. You could potentially be harming your fish or your bacteria. So you have to optimize these systems for all three living components. You have your plants, your fish, and your bacteria. Additionally, since it's inside a greenhouse environment, you have less exposure going out too. That's a major benefit. There's no effluent from our technology right now. There's no waste whatsoever. So we're not having to manage sludge. But that's not an issue of where do we dispose of this kind of stuff. How's the environment being impacted? There's very little risk of our fish being exposed to the environment too as well because they're completely closed. Okay. And then unlike warm-blooded food stocks, cultured aquatic species, and you guys are probably familiar with this, cultured aquatic species are low probability vectors for zoonotic disease. And I've actually consulted and talked to some groups over in Thailand where they use warm-blooded animal waste to feed the tilapia that they're raising in ponds, and then they have, in this case it's chicken waste. They use chicken waste to feed the tilapia, and then they eat the tilapia. And chicken waste is one of the dirtiest things you can imagine. And then they're actually raising plants right on the shore too. So everyone has a different standard for cleanliness. But if it's that or not eating, I guess I choose that. Okay, so areas for improvement: dependence on fish meal. And I'm sure everyone here's well aware of the major issues out there with fish meal and overfishing. And the fact that there's a large demand for it, and it's a resource that's finite, it's limited, and it's actually already starting to show some stresses in the market. Difficulties with large-scale production of fruiting vegetables. This is something that maybe you guys aren't familiar with. The first-generation aquaponics technologies, for the most part, have proven very successful growing leafy greens. However, that can be in niche markets. I mean, it's proven successful in a number of other markets too, but it's most successful in niche markets. Now, when it comes to greenhouse practices and all these other elements around the economics of running a greenhouse business, you have to be able to utilize your verticality of your greenhouse and look into plants that are going to make better use of your space, so you get higher productivity per square foot. And one of the crops that do that are your fruiting vegetables for the most part. Your tomatoes, your peppers, or at least this is our belief. The tomatoes, the peppers, and cucumbers, things like that. These have all proven effective in aquaponic environments, but nobody has really gone all the way and said, this is the way we should roll out a whole production facility for this product. And so there's still a lot of design to go into the most effective way to utilize your space at growing these other types of vegetables and showing that this is an economically viable business plan. And so that's an area for improvement. And there's a lot of demand for fruiting vegetables. Okay, acidification of the water due to the nitrification process. So if you remember back when I was going through the stoichiometry and the chemistry, kind of the boring parts, you might have remembered that there's hydrogen being produced from the very first oxidation of the ammonia. So that hydrogen is constantly acidifying the water, reducing the alkalinity of the system. These plants need high alkalinity, not as high as some fish, but high alkalinity, high hardness levels, calcium carbonate levels, to grow effectively. And one of the things that takes place is every single time you process that nitrogen, you're taking away from your calcium, magnesium alkalinity. So there's got to be better methods for handling the processing of the nitrification and managing the hardness of the water. There's been a decent amount of research done. That's well understood now. It's just a matter of rolling that into your business plan. It's not really that hard. Here's an example of what I'm talking about. So for each gram of ammonia that's being processed biologically, 4.57 grams of O2 are required. That's okay, O2 is free, it's available. But what happens is you can visualize, when the hydrogen produced, you can visualize this as taking up 7.14 grams of alkalinity in terms of calcium carbonate equivalents. If you guys don't know what that means, I always like to go back to the global warming equivalents or the global warming factor. They say that methane is 30-something times as potent of a greenhouse gas as CO2, and they measure that in CO2 equivalences. So this is how they're measuring alkalinity or hydrogen production, alkalinity loss or hydrogen production in terms of CO2 equivalents. Okay, and it's a challenge for treating pests for both the plants and the animals. One of the first things recirculating aquaculture groups would do for treating, let's say, ick on an animal would be raise the salinity, raise the ppms, or maybe even apply, you hear of copper and different things like that being used. Well, these are sensitive issues around the hydroponic side of this equation. If you raise the salinity too high, you're not going to grow any plants, and because the whole the mechanism for plant uptake is osmosis, and that can really mess with the osmotic pressure for uptake of nutrients. And then additionally, if we start to see pests, and actually we've tested a number of natural pesticides. We tested neem oil, a couple of different things like that, and applied it to our plants, and then of course eventually it makes it back down into the water source one way or another, even if it's only in small concentrations. And that has shown to have some negative effects on our fish production. Okay, so the Center for Sustainable Aquaponics. So, like I said, what our function here is to produce component technologies and a new business plan for unrolling the future of aquaponics. And what we're focusing on is technologies that can produce a number of different types of crops and a number of different types of markets based on very simple premises, very simple designs and usage ways of using it. So this is actually all stuff that was done with our first generation prototypes, and we're actually moved away from a lot of this, but I wanted to explain what's going on here. Our systems are basically raceways, and the 10,000 gallon raceways. They house 2,000 rainbow trout, and And we grow them out to, I think right now we have some 16-inch rainbow trout in there. And we're using a different type of technology where we're utilizing tube culture techniques, which house less water. They make more, if you have a limited water constraint with, as far as what your makeup is or your total volume of water you can hold. These house less water than other technologies, and they also allow us to use our hydroponic components in a number of different manners. We can use our hydroponic components using NFT techniques, which is nutrient film technique, which is very common in hydroponics, where nutrients go in one end of a tube or a gutter, and they travel all the way through, and it's a continuous flow, and it's constant sequestration. Or we can run ebb and flow, and actually I don't think we have any examples of our ebb and flow systems here, but we can run ebb and flow, which means you're filling in this tube area with water, and by doing so you're evacuating that area of its air, and in that air there's going to be all kinds of respiratory byproducts, which are CO2, methane, different types of sulfurous gases, all products of just natural biological processes that are taking place within the root zone. And so you flush that out by filling in that void with water, and then as the water leaves, it escapes, air is forced to pull back in, and by doing so you're actually aerating the roots. And ebb and flow technology is a faster means of producing plants. It's also supporting longer, or supporting healthier root growth in a lot of cases. Well, when done properly, it supports longer, healthier root growth, which means you can have longer lasting plants in the system. So now you can start moving into the perennials, your flowering crops, things that take a little while to grow. And now we're starting to move into the fruiting vegetable production side of things. So that's one of the benefits of what we're trying to do here is we're trying to develop technologies which are adaptable for any type of crop we want to put in. And we've designed specific facilities for that one type of crop production, or two types of crop production. So here's some just pictures of what we did over the summer. This was our very first summer getting started last year, and we had different zucchinis, and you can see one whole side of our greenhouse was a wall of tomatoes, a sea of green tomatoes. We experimented with just about every single type of lettuce you could imagine, because that's been tried and true in the industry. Leafy greens are heavy nitrogen, well, I shouldn't say heavy nitrogen feeders, but they're nitrogen feeders. They require more nitrogen in comparison to other nutrients than a lot of crops out there. And so, because the system is so nitrogen favorable, it's producing so much nitrogen, it makes sense to do leafy greens. However, there's a myth out there that you can't do fruiting crops because they require a wider range of nutrients than your leafy greens. Well, that's simply not true. The nutrients that are available, well, that might be true to some degree, but the nutrients that are available inside the aquaponics system support those plants. And we do very extensive studying. We do testing daily at this point on the changes in our water quality parameters. And we've actually spent a lot of time doing literature review to make sure that this is true, that you can raise a tomato under the same kind of conditions that you see inside an aquaponics system effectively, or a cucumber, for example, and you're going to get the same kind of production out of your lettuce. And most systems that are effectively raising lettuce, with a small modification, they're able to now effectively raise all these other types of crops if they have the right hydroponic environment, which is what we're trying to develop. And you can see this is just different pictures of lettuce and fruiting crops that we have. Here's our mission statement. The Center for Sustainable Aquaponics seeks to address the issues of food security, environmental sustainability, water resource conservation, and conservation by developing economically feasible aquaponics prototypes and component technologies. And so our current work is in developing cutting-edge prototypes for commercial-scale aquaponics. These prototypes are basis for consultation and developing down the road. Right now, we really just jumped head first and just try to get some first-hand experience about what's needed in the industry. Let's just start doing it, and then we'll modify it. And so that's what we've done with our first prototypes, and now we're moving on to our next ones. So some of the areas that we think are absolutely essential for the future of commercial scale aquaponics is research into new feedstocks to minimize the demand for fish meal. Has anybody ever read anything by Rosalind Naylor? She's a pretty famous scientist at Stanford University in the food security group, and she focuses her projects around sustainable fisheries. And so what she says is some forms of, and this is actually taken from, oh, I don't know, it's actually taken from Science in 2010, or 2000, but what she says is some forms of aquaculture relieve pressures on ocean fisheries, but the opposite is true for others. The net result of global aquaculture production still adds to fish supplies. However, if the growing aquaculture industry is to sustain its contribution to worldwide fish supplies, it must reduce its dependency on wild fish inputs and feed and adopt more ecologically sound management practices. And I think this is something most of you already know, but this is definitely a hot topic within the aquaponics community because these guys are focused on sustainability, but also just within the aquaculture community because they're also focused on sustainability, but they're also, there's a lot of economics at stake here with the rise in demand for feedstocks, for fish meal. So some of the research that we're trying to do in here, and actually we have some of the researchers here, is to devise new nutrient inputs into these aquaponics systems. This is not only for the fish, but for the plants. What we'd like to do is move away from the conventional engineered fish meals that are for the fish, and focus on ones that are both balanced for the fish and for the plants. Ones that take on a number of other types of different nutrients. Fish meals mainly crude protein, some potash, and actually there's a lot of salt in it. That's actually pretty bad for the system. Salt compounds, sodium, but and then also fat. Well, what we're looking into right now are some different types of vermiculture practices that we can do to raise bugs that can become part of the fish meal or just completely replace the fish meal. And there's a number of articles out there that say that these black soldier flies, has been tested, these black soldier fly larvae, the grubs, the little maggots, they can actually replace, I have it up here, up to 50 or 25% regular feed. I've seen 100% in some studies. Now whether that's applicable for every fish, it's hard to say, but they could certainly replace up to 25% of regular fish feed if you get the production up. And the beauty about these guys is that they're very vigorous eaters. They'll consume just about anything. They're composters. So you can use other forms of farm waste. There's people raising these on poultry waste, or there's people raising them on swine waste. There's people raising them on regular just compost. You can raise them on just about any kind of waste. Obviously, garbage in, garbage out. You want to give them good waste, but they'll eat stuff that's otherwise considered a byproduct or a waste product of another industry, and now they create a beneficial food source for this industry. And some of the beauties about them is they actually they take on a number of different types of nutrients. They take on potassium, phosphorus, potassium, calcium, magnesium, manganese, iron, boron, zinc, copper, and aluminum. And these are all nutrients essential for plant development. There's 16 essential nutrients for plant development. These are broken up in different categories, macronutrients and micronutrients. A lot of your micronutrients you don't actually have to worry about. You don't have to worry about supplementation of this. They come in through the feed, and they come in through the water source, or they come in through other means. The big ones are your calcium, your magnesium, your iron. These two are pretty big, but actually we've been pretty lucky in the fact that we've only had to really replace the potassium. The four most common nutrients that are made up in these aquaponics systems that are supplemented in the aquaponics system are potassium, calcium, and magnesium. This got combined as one because they kind of come together. Phosphorus and iron. Those are really the most common ones. I know it's like five, but like I said, calcium and magnesium are oftentimes found together. So these guys take on that nutrients. Another beauty about them is that you can actually process these. You can process this and store this. You don't necessarily need to have live grubs on demand for when you're ready to feed. And what we're trying to do as part of our philosophy, what we're trying to develop in our technology and our business practices, actually we want to minimize the number of inputs that have to go into these systems. We want to minimize the number of places you have to go to keep one of these systems running, so that we can open up this technology to markets that don't have all the infrastructure in place. They don't have the fish meal in place. They might not have the fish hatchery in place. There might not be fingerlings available to bring on these animals, or to start these systems. So this is all something. This is one of the many different projects we're working on that incorporate that philosophy that we're focusing on. Another area that's really popular, and this is actually just one out a number of different groups that are trying to do this kind of stuff, is algae production. Algae production for the sake of feedstock is kind of popular. I think you guys might actually have some more expertise in this area than I. There's been problems trying to convert the fish, the feed, trying to convert the animals from a feed that's based off fish meal over to an algae-based algae-based feed. There's certain limitations as to how much you could supplement that feeding with, and some animals won't take to the feed. So this is an area definitely that's still. These are both areas that need a lot of development in, and I'm optimistic about both of them. There's also a number of other groups around that are trying to make fish feed out of spent barley from breweries and different things like that. So you guys might have even heard of them. So it's a very popular topic, but it all revolves around getting away from the fish meal. Okay, here's a major area for improvement: digesters and bioreactor technology. So whenever I say bioreactor, I'm talking about the component of the aquaponics system that strictly takes the nitrogen in the form of ammonia and converts it to nitrate, NO3. And digestion's a little bit different. Digestion's generally thought of as an anaerobic process, and what we would like to see is that we actually come up with aerobic processes that use a number of different types of biological elements to unlock nutrients such as phosphorus, calcium, iron that wouldn't be available. They're not mineralized in the water. They're not available to the plants, and we digest that from the fish waste itself, and we turn that and we mix that into our nutrient solution. The bioreactors right now for aquaponics systems tend to be wasteful. A lot of nutrients are removed in the form of solid waste. That solid waste is not always, or it hasn't always been proven to be of value to aquaponics. In some cases, people believe that it just has compounded too many salts to be useful in any manner, whether you want to put it onto a garden, a soil-based garden, or whether you want to dilute it and use it as a foliar spray to supplement nutrients to the plants, because they can take up nutrients through the leaves. Some nutrients, not all. Well, as it turns out, the managing of the biofloc, or cooling of the biofloc, is a major issue. It's something that UVI used to have to do twice a week. They have to take out all their substrate and all their media for the bioreactors, clean it, and then put it back in. And that causes swings in production. It causes all kinds of problems. And inefficient bioreactors actually, they bypass part of the nitrification process, and they go straight to denitrification, which now means we're taking nitrogen that would be available for plant growth, and we're off-gassing it. We're turning it into gas. And actually, the N2 gas, as you guys know, is a major issue with aquaculture operations. Fish are highly sensitive to anything above saturation with nitrogen gas, and I think it's as little as 3% can start showing detrimental effects on the animals. It might even be lower than that for all I know. So what we're trying to do with our next generation, this is actually not a picture of our own bioreactors, we don't have them up on this display. What we're trying to do with our next generation bioreactors is utilize more of the fish waste. Our ultimate goal is to get down to zero waste, where we have no sludge. And as it is right now, we actually have no sludge, but we're just running prototypes. We still have to get our bigger systems up and going to be able to demonstrate that. But our ultimate goal is to have no sludge come out of the system. And we believe through proper management, proper stocking of different types of crops that require different types of, not require, but which will take up or remediate different types of nutrients from the effluent, that we can actually achieve that. You know, it's a fancy algorithm knowing exactly what the crops take up, what you're putting in, and what your homeostatic state is inside your system. And these things do kind of go into homeostasis. They find a balance. It's not just an equilibrium. You throw them out, and they kind of want to go back. It's a biological, it's a living organism. It's a living system. So our new technologies, what we're trying to do is we're trying to utilize all that fish waste, take out all the solids, process them in a different manner on a parallel branch of our system, bring that mineralized nutrient water back into the system instead of wasting it or emitting it to the environment, and then be able to grow a number of different crops, even better yet than the previous technologies, because we have the additional nutrients available, and it's a wider spectrum. So we have not only more nutrients for a specific type, let's say nitrogen, instead of being 120 ppm, we're up to 220 ppm. And instead of not having, let's say, calcium available, we now have it available because of the practices that we're doing. And this allows us to do these other types of crops. This is an example of last summer. This is our very first time trying to grow cherry tomatoes. And it got to the point where we were growing so many cherry tomatoes, we were picking 5-gallon buckets just to be able to reach around, because part of the pruning process, and be able to walk around our facilities because we didn't really know what we were doing in terms of planting. So mineralizing and digesting nutrients in a more efficient manner is going to reduce the environmental footprint, and it's also going to increase our production. So it's going to look good. It's going to be a good thing for us. Nutrient budgeting. So I just said a little bit about that. What do I mean about nutrient budgeting? How does plant type and stage of growth correlate to nutrient sequestration in an aquaponic environment? So this question, I'm going to break down what this is asking. How does the type of plant that we have, whether it be lettuce, tomato, cucumbers, and how old it is in our system, how big it is, more of a biomass than age, how do those compare with its rate of uptake of nutrients from the system? And once we have a strong understanding of exactly what these plants do in this aquaponic environment, the tube culture aquaponic environment, because every culture might be a little bit different too. And hydroponics is different from aquaponics because there's different types of lockouts and things like that. These plants might not grow as fast in one environment as they would in the other. And actually, we've actually shown that some plants grow faster in aquaponics than they do in conventional soil-based systems because of that ebb and flow feature. Well, I actually can't really nail down why it is because there's so many different things we're doing. But we believe it's because of the ebb and flow feature, the biodynamic environment we create at the root zone, the symbiotic relationships that are taking place at the root zone that are allowing nutrients to be more readily absorbed by the plant or just even available in general, as opposed to if they were inside of soil, it might be locked up in another type of mineralized form. So what we'd like to do is be able to say, for this mass of plants, let's say 200 plants, or let's just normalize it to 100 plants. For 100 pepper plants at this age, this is the type of sequestration we expect to see. And now we can throw this into an algorithm and say, these are the inputs that we're putting into our system. We know we can project or predict what the output should be from the aquaculture component at any given time, and say, what is our sink and what is our demand and what is our sink? And say, okay, these two have to be in correlation with each other, and we have to look for anything that's going to blow up. Maybe it's sodium. Now we have to think, okay, let's bring on some spinach, because spinach is actually one of the crops that take up a lot of sodium. There's a lot of sodium in the fish meal and the fish feed. So that builds up over time, and it could potentially cause, it could be detrimental to the other crops that are too sensitive to sodium, too sensitive to salt. So by being able to say exactly what the composition of the nutrients is inside our system and knowing what the uptakes are of our different crops, we can now say we need to go 30-something% tomatoes, 22% peppers, and the rest needs to be spinach and lettuce, because this is the nutrient makeup that we have. And we believe that once we have enough time to observe these systems and get them into that homeostatic state, we could just nail down a constant production. We're going to be weekly this much tomatoes, weekly this many peppers, and it stays the same. And then we would adjust it for different markets. So we'd say, okay, we'll just go with a totally different crop diversity for a different market, because this market doesn't have the demand for tomatoes. Okay, so I guess the ultimate question that we're trying to get at is, what is the proper way to plan and balance nutrient loads to optimize productivity and profitability? And this is something that I believe is second-generation research. There's some groups down in Florida that did some great research on this, and there's some groups in Alberta that did some great research on this, but this wasn't the focus of the research done at UVI. They were pretty plant limited, actually, as to what types of crops they can grow. And then how do we manage the pH dropping? Well, that's actually so closely correlated to this, that's not even a separate question. We made this back in October, so I forgot to take that out. Okay, so improvements over the hydroponic technologies, the current hydroponic technologies. Here are 3 different examples of different types of hydroponics that are being used in aquaponics today. Hydroponic technologies are being used in aquaponics today. One is the raft technology. This is actually kind of a bad example, but it is a good picture. You can see there's a grasshopper on there. It's low to the ground, And there's a lot of pests as a result of being low to the ground, but that's not a deterrent to move away from the raft technology. It's really effective at raising leafy greens, has low overhead, low capital costs, and it's low maintenance as well. If a pump breaks, these plants are submersed in water, they'll survive for a long time, so the risk is minimized by that. Some of the things that you don't see here is there's a lot better practices than what a lot of aquaponics groups do to raise these plants. It's actually a fairly labor-intensive practice, having all these pots and substrates and stuff like that. There's some things that recent groups have adapted from the hydroponic industry where they're creating plugs now, and you can go and harvest a whole area, a massive area, an area the size of this room, in a day, with one person just going through and cutting these plugs off these rafts, these styrofoam rafts, and they can seed it also. They can seed it and transplant it in the same amount of time. It's actually quite quick, and there's no additional materials that are needed. This was, like I said, our first generation approach to growing tomatoes in tube culture, and that worked out fairly well. And we actually have a lot of improvements over this current design, but ebb and flow in tubes is where we believe the future lies with fruiting crops, at least, with greenhouse technologies. And then the vertical towers. This is something that generates a lot of hype these days, but I still don't understand how these are going to work out in a very intensive greenhouse environment. They're definitely utilizing the verticality of the greenhouse, and it's great because a lot of the crops that they grow are low light intensive crops. They grow a lot of lettuce. However, they do grow a lot of higher light intensive crops as well, which would be your strawberries and things like that. And your fruit crops generally just have a higher demand for light, for everything, than your leafy greens. And the problem with going vertical in a greenhouse is now you have to deal with row shading. How are you shading different rows of your production by going upward? Because especially here in Colorado, we're at 40 degrees latitude, right? That's the right one. and during the wintertime, we have very, very low sunlight. And if you were to go vertically inside your greenhouses, you could potentially be only growing crops on the very south side, and all the other production would be severely decreased due to the rate of photon absorption of the plants behind that in the shade. So there's a lot of question as to how to optimize the hydroponic component for profitability, or more or less production per square foot. This is the way people think about things in the greenhouse industry: is how fast can we grow these things, and how much production can we get out of it per square foot. So there's a number of areas there that are open for exploration. If you search hydroponic techniques on the internet, you'll find millions of pages of people trying different things. But there are only a few groups out here, and Colorado has actually a pretty disproportionate number of them, of commercial scale aquaponics systems, or near commercial scale. And there's only a few groups that actually have shown the viability of aquaponics in a greenhouse environment. These greenhouses are costly from a utility standpoint. They're great in the sense that you have the natural lighting and everything like that, but you also have very low absolute values in a greenhouse. And during the winter seasons, where you would want to be growing fruiting crops, I think, because that's the benefit. Well, you'd want to be growing crops either way, but fruiting crops are desirable in a greenhouse environment during the wintertime because it's a niche market, something you're producing locally that you would otherwise have to get from Mexico. To keep those greenhouses heated to that high temperature, that's a very costly thing to do. So in summary, aquaponics is an up-and-coming field of science which demonstrates commercial applications. It actually has been proven in some applications to work, but there's no system that's out there that spreads all the way across the field of, all the way across the market and says this works in 80% of the market. So this works in 70%, even 50%. That'd be huge. We're traditional agriculture. They're able to make that happen in a lot of different ways. Even traditional hydroponics are able to make that happen. It offers solutions to problems faced by traditional agriculture methods. We went through all that: the environmental degradation, and the resource reliance on of regular agriculture. And then research is still required to master commercial applications of the science, and that's where we stand. That's what we're trying to do. Okay, and then I'd like to make some acknowledgments. I'd like to acknowledge Mountain Sky Group and Nourish the Planet, which are the groups that I'm partnered with, and they're the ones that make this all happen. And they have a very unique model, and they're trying to develop food and ag industries in an incubator-like manner. And their goal is to enable 1 million ecopreneurs by 2016 to teach the world to feed itself. So this could, an ecopreneur could be anything. This could be a village in Africa. This could be me. This could be another company similar to mine. And they've done a significant amount to help us out, and they're just world experts in what they do. So if you have any questions, you can definitely take a peek at what they're doing. If you have any questions about us, we're actually developing our website right now, so you have to kind of come to me at this point, and I'll give you guys some contact information. You can look at what's going on. So, general questions. I'd like to open it up.
The system that size that you were just showing us, how long do you think it takes to cycle it out?
To cycle it out? Great question.
Scratch.
Great question. I'll go back to the, we actually have dates on ours, on the graph. But generally speaking, under the proper conditions, temperature and pH mainly, you could get these systems up and going in 60 days. And I actually meant to touch on this a little bit more. One of the things that we're doing, and actually we have a group of interns working on this right now, they're doing a great job, is we're studying how to fishless cycle a system. And either way you look at it, you have these 60 days, but if you bring fingerling fish into a large environment, let's say you're doing what the UVI system does, where they have 4 identical sized tanks, and they're putting small fingerlings into this large tank, and the nutrient value of that tank is pretty low, individually speaking, you know what I mean? So one of the things that we're trying to research is how do we synthetically bring these systems up to speed? So we have the whole biofloc that we want, the whole process is there, but it's fishless. We just add the ammonia to the system, we get it into place. We even can have plants in place. It's great to have the whole thing in place prior to bringing the fish in. Then you bring the fish in, and you wean back on that supplementation until you get your entire fish production, which is staggered. In our case, we're talking about having 12 raceways. They would have the different size raceways. They're not grow up the entire life stage, or the entire 12 months inside the same raceway. We obviously move our fish around a little bit, but we minimize that. The idea is though that you would have a constant nutrient load for the system, by bringing it up with these synthetics, and then as you get the fish in place and you start to harvest and restock, your perturbation to the system is so minor that you don't really see it on the plant production side. And these plants work in a wide range of nutrients. These plants can go down to, I've seen plants at 20 parts per million nitrogen before, and green and healthy. And if you ate it, you wouldn't know the difference. They just grow slower potentially. I mean, that's generally what happens. They just grow slower. So you slow down your production, but the spikes in the nutrients for the plants don't seem to have nearly as big of an effect on the system as the spikes in the nutrients for the fish. So either way, you want to minimize those spikes. You want to have really balanced load with demand, but you could do that in a very fast manner, so that you're actually putting fish in 60 days after the construction of your system, and 60 days after the construction of your system, you should be able to put plants in, and you're starting to harvest those plants, depending on what kind of crop it is, anywhere between 35 to 80 days from that first 60 days. And so halfway through the year, you're already in a production mode, and your fish are still small. You have to wait you can't beat Mother Nature with the fish side of things. You have to wait the 12 months. And we've actually been able to raise our fish from 3-inch fingerling size to 12-inch, I think they were 1.15 pounds in 11 months. And now they've been in our system. Our first experiment we ran is now 13 months in operation, and they're up to 16 inches. So these are really healthy looking fish. They like this environment. It's mimicking nature to them. Yes?
Regarding the fish, what sort of advantages or challenges have you had by choosing rainbow trout versus a hardier fish like tilapia?
Excellent question. Excellent question. Let's just do challenges for the time being. Okay, challenges being, obviously the oxygen demand of the rainbow trout is significant compared to the tilapia, and we do not supplement oxygen. Everything we're doing is passive. So there's very little supplementation that goes on in the entire system. Like I said, we might add calcium here and there, and we have added some iron and some potassium. But that's aside from the topic that we're on. The oxygen is a major issue. We try not to let our oxygen ever drop below 5. And what we've seen, actually right now, they're hovering right around saturation. So we have really great oxygen in this kind of temperature, which our water temperatures are ideal for rainbow trout grow out, and we're growing inside of a greenhouse environment. They're ideal right now. They're right around, I shouldn't say ideal, but they're within the ideal range. They're right around 12 degrees C. And we have pretty good feed rates at that 12 degrees C. We get down below 8, which we did last winter when we were more conservative with our utilities, and we drop off on the feeding. You know, the animals just won't touch the feed at all. And that's been a problem. They're definitely more sensitive to adverse water quality. So you know, they're more sensitive to the nitrite. They're more sensitive to the ammonia. They only go down they only feed at pHs. In our system, they won't feed below pH 6.3, and we don't let our system get there anymore. But you know, we have tried just to see the strength of the system. You know, how much you can stress it. And so, you know, the feeding has been a challenge because you got to maintain optimal water quality. It hasn't been a challenge for us because we're not stressing our system. We don't have terribly high stocking densities. I told you we stock at 2,000 animals per 10,000 gallons. So, you know, I think the overall outcome ends up being a little bit shy of 0.4 of a pound per gallon. But I could be wrong. Don't quote me on that one in terms of its stocking density. So, actually, I'll probably tell you, but they're pretty good with stocking density. That hasn't been an issue. Water quality hasn't been an issue. Dissolved oxygen has been our concern. Parasites haven't been an issue. We haven't seen, you know, most fish farmers see ick outbreaks during the spring. Hasn't been much of an issue. We don't know why that is. I want to research and find out whether that has something to do with the actual electric conductivity of our systems. Benefits. The benefits are they're available. You know, the tilapia is available and all, but these guys are easy to work with. They're very easy to get a hold of, especially here in Colorado. You got Idaho, Washington, Colorado. These are good states for rainbow trout production. And every state has rainbow trout production for the most part. It's just been easy to get a hold of. They're affordable for us. There's readily available feed for us. The whole industry's built up for us. So we're actually piggybacking on a lot of work that everyone else is doing. Okay. Any other questions? Yeah?
Yeah, I was curious on the, you have big chillers, I guess, to run that water through and keep it at 12 C?
We don't chill. We don't chill, not even in the summertime. And we've actually let our temperatures creep up to above what we'd like to see them at. You know, a lot of people say, you know, get to the 70 range, your trout are done. And, you know, that's, depending on how intensive you are, how stressed they are, that could be true if you're doing stuff that's wrong. And you know, obviously you're making them more susceptible to an outbreak. But like I said, our whole focus is to create these really healthy environments for both plant and fish production. So our focus is just keep it healthy, and then when we see these small stresses, they're not as much of an issue. So over the summertime, we've reached 20 C, which is, you know, toward the upper limit. They'll back off of feeding at 20 C. They won't feed anymore. But that might just be for you know, a week period. And these animals, these are fat-looking, healthy-looking animals. They can go 2 weeks without feed easily, and we don't do that to them, of course. But we have confidence that they could back off of feed for a while and be just fine. So we might have a week or 2 week period. It wasn't continuous last season. We just maybe had a week last season. And this is only our second season going into it. But we were also making a lot of greenhouse revisions and renovations, and our greenhouse is chilled to keep the temperatures low for our plant production. The greenhouses really should never reach above 40 for what we're trying to do, 40 C. And so at 40 C, we believe we have a system design that's conducive for rainbow trout, because we're ebb and flowing for one. So a lot of our water that's outside of the main body of water is only outside of it for a short period of time. So that's like the radiator of the system. You know, it's collecting heat, and it's great in the summer. It's great in the wintertime because it's collecting heat in the wintertime from the passive solar that we're receiving, because our greenhouse today reached 40 C. And it's probably about that time of the year where we got to turn the fans on again, the exhaust fans. But, so the water temperature is actually being kept from freezing by the radiative properties of the hydroponic components. However, in the summertime, it works against you, and you're heating it up. So we use ebb and flow technology, but we only flood here every once in a while to minimize the amount of water that's out of the system. So we have all the water kind of contained in giant thermal mass. Okay. Yeah, keep going.
One more.
We can meet afterward, too.
You're talking about majority, well, everything you do is consumption based, and you're talking about sustainability. Have you ever thought about, or what was your thought on the ornamental production market? You know, to maximize, because you have the space to maximize efficiency and turnover. What about the ornamental production? There's a lot of reduced shipping, emissions and stuff like that.
Yeah, and there's definitely a market for that. There's people that have come to us and said, what if you could do these here? That is a very attractive thing to pursue. It's not our focus. Just what we're really trying to develop is a food production model. That's what we'd like to say is the most sustainable food production model in the world. And that's a bold statement, but that's our mission. That's our goal. And I think that one of the ways that we can really advance this technology is if the people that are hobbyists, or aquarists, or whatever, decide to take it from whatever level they're doing right now to some large-scale production like this with ornamental fish. The science is essentially the same, and should they do that, I think it really could drive a lot of innovation. So I welcome the idea of it, but it's just not our focus. We're trying to stay pretty narrowly focused right now because it's one of those industries where it's hard to gain traction and credibility. There's so many people that are doing a million things all at once, and they're not doing any of them great. They're just doing them mediocrely, and we'd like to just focus on doing one thing really great, which is our specific model of food production.
All right. Well, thanks for coming.
Thank you, guys. I appreciate it.